Welcome. It's good to see all you guys here. We're all coming back from lunch. Always an exciting part of the day. And I'm here to talk to you today about FDio, FDio, the Fast Data Consortium. So we've all been deeply involved in the evolution of more dynamic networking. Everybody here is here because we're working on OpenDaylight. We're providing the premier controller for how people want to manage their networks. One of the things that I think is sunk into a lot of us, if not most of us over time, is that your controller is only one piece of the puzzle. That it only actually gives you one chunk of what you need to actually get where you want to go. And the other chunk is you need a fully programmable data plane. And that data plane has to be performant, it has to be scalable, it needs to be stable, and you need to be able to program it to do the entire array of tasks that you need it to do in order to realize some of these more dynamic network use cases. So when we all start looking at existing data plane solutions, particularly the software data plane solutions, they've got a wide array of difficulties and problems. So you have challenges with performance, you have challenges with scale. They tend to have a very complex model that requires you to pay attention to a bunch of stuff that you don't usually care about in the course of programming them. As you try and evolve forward, you discover that the evolution is difficult because you have to get patches into not one but two monolithic code bases often. You discover that you end up having deployment issues because you have to match kernel versions to the sets of features that you want to have. And as you know, users are very particular about the versions of kernels they want to deploy on their servers. And this makes everything extremely challenging. Now, at the same time, for those of us who've actually operated networks, you'd like to know things like, has this whole thing been tested end to end? And do we know that this framework actually scales and performs in realistic scenarios with realistic traffic patterns? You'd like to know, for example, that if you're a hardware vendor, someone who produces not necessarily boxes but chips, that there is space for you to innovate. Because if you as a chip vendor, a service system on a chip vendor, et cetera, if you have some cool thing you can do to make the network go faster, but the semantics with which people can program the network preclude that innovation, you're stuck. And so it cuts off an entire stream of available innovation that we think should actually be open. Additionally, you get portability across platforms, optimal use of microarchitectures, and for those of you who've actually operated networks, instrumentation. You need to have counters for everything, so when things go wrong, you can track down what's happening. And that level of deep instrumentation, and it needs to be semantically meaningful instrumentation, because if I have a pile of counters that don't map to anything I care about, and I have to figure out how to map them back, I might as well not have them. So to provide a better way, a better solution, the Fast Data Consortium, FDio, usually pronounced FDio, was launched, I guess, a little over 2 weeks ago at this point. It's a Linux Foundation project. It is very much like OpenDaylight, a multi-party, multi-project consortium. So there are multiple members, there are multiple projects, anyone can bring a project, anyone can rise to being a committer via meritocracy. It should look very, very familiar to those of you who are used to participating in OpenDaylight in terms of how it's governed. The difference here is the scope that it's working in. So the scope that Fast Data, that FDio is looking at, is not the controller scope that we're all familiar with in OpenDaylight. It's I/O services. Now, the I/O services we're most familiar with is networking. We think about things like, how do I get a packet from a NIC to a thread? Then once it's there, how do I process it? How do I do some of these sorts of actions like classifying it, transforming it, prioritizing it, forwarding it, or possibly terminating it on the box if it's a packet that's destined for me. And then management agents, the things that run locally on the box that allow you to control this I/O. Now, we all think in terms of networking, but FDio is broader than that. FDio includes all I/O services, not just networking, storage, other kinds of I/O. All of those are within the scope of FDio. And this is actually really germane. If you look at the way the world is evolving, storage, networking, all different kinds of I/O are getting closer and closer together as time goes on. And so it makes sense if you have a good framework for doing these kinds of tasks, a good framework for handling the getting things from hardware to threads, a good framework for processing the things once you have them on threads, that is faster than hell, you might as well take advantage of it. So at the core of FDio is VPP, Vector Packet Processing. It basically gives you a framework and actually a fully working vSwitch and vRouter for handling the packet processing tasks. Now, it uses DPDK for its network I/O. Basically, it is extremely high performance, extremely high scalability. It runs purely in user space. So as long as you have the basic functionality in your kernel for UIO so that you can support DPDK, it doesn't care. It'll do whatever you need done. It uses a directed graph for packet processing. So it's a packet processing graph technology. And this is something that's a fairly mature code base. This code base has been alive inside Cisco since 2002. It shipped in multiple products at volume. It shipped in embedded boxes. It shipped in server products. It's multi-architecture. It runs on ARM, PowerPC, Intel x86. Just fine on all of that. And as you'll see as we go forward, it's been carefully architected to make it possible to take advantage of any hardware accelerators that you have while still continuing to do your job when you don't have them. So this is just a very simple picture of where this lives in the overall stack. It lives right down near the bottom with, just adjacent to network I/O. VPP lives right there. We do use DPDK for network I/O currently. DPDK does a great job of getting the packet from a NIC to a thread. We don't use the DPDK packet processing mechanisms because what VPP does, it actually has a lot more functionality and it has a lot more performance. So I mentioned earlier that FDio is a multi-project consortium. VPP is not the only project there. So this is an example of some of the other kinds of things that we would foresee people bringing as projects. VPP itself is very modular. As you'll see as we get a little further on, anyone can write a plugin, drop their binary plugin into the plugin directory, and load their graph nodes into the graph, manipulate the arcs in the graph node, and therefore implement whatever data plane feature you need without necessarily having to change the core VPP code. And so this gives you a very natural technical architecture to move to a modular project architecture, governance architecture, similar to what we have at OpenDaylight, where if I want to go and get together with a bunch of people to work on a load balancing feature, we can come together, we can put a project proposal forth to the TSC at FDio, and we can get that project approved and go work on a plugin that will do load balancing. Similarly, for some of these others, firewall, IDS, host stack. If you're a chipset vendor and you would like to be able to take advantage of your hardware, you can actually bring a plugin that will essentially do your hardware's work, replacing some of the work you would do in software graph nodes, and then have an arc that departs to go to the software processing pieces that you don't do in hardware, thus giving people better performance with your hardware present, but also allowing things to continue to function when it's not. This is particularly important when you're doing things like building VNFs, because it's great if you have accelerating hardware for your VNF, but if it's not present, you still want it to work, if you've had to burst up beyond the specialized hardware that you have. So control plane, FDio is completely agnostic about control plane. You can bring management agents for any SDN protocol you would like. We're welcome to all, we welcome them all. And all these other sorts of things that you can see as projects. And frankly, I imagine there are people in the room who could think of others. Other kinds of things you wish your data plane could do for you that you just haven't been able to see your way clear to yet. With FDio, you can bring them, you can do them as a project, you can utilize them, you can get them hooked up to the broader ecosystem of SDN, NFV, and cloud. Yes, question. Mm-hmm. Mm-hmm. So think of it this way, and I'll sort of describe the process which you would do this because it tells you a lot. So let's say that I did want to bring load balancer features. Some of us get together, we'd like to write some graph nodes that when a packet comes in for the VIP, it gets shunted off to our graph nodes and we do load balancing behaviors. So I'm going to do this in the context of FDio. There's obviously a context where you could do this behind closed doors. But in the context of FDio, we'd get together, we'd put together a project proposal, which you will find looks remarkably like what you would do for a project proposal for OpenDaylight. We would get our project approved. As we're doing our development work, we would have to install a package with headers, so the VPP dev package, so we have the headers. But other than that, we don't need the VPP source. We can just write the source for our plugin, build that plugin to a binary.so, and the process of installing it is literally dropping that SO in a particular directory. Then when VPP runs, it finds that plugin, it loads the plugin, runs through initialization, and that plugin influences the graph by introducing new graph nodes, by wiring things differently, exposing low-level APIs that people can use to control your graph node functions, just as if they were part of the core VPP. And so it is a really even playing field for you to add data plane features without having to go and try and get your patches into some upstream code base that may or may not be interested in the thing you're working on, in this example, load balancing. Did that answer your question? Okay, good. Yes?
Could you contrast this approach with OpenVSwitch implementation? Let's say I have OpenVSwitch and I have a piece of hardware that allows me to offload it. And I am able to express most of the services like load balancer, maybe
some
other services in OVS pipeline.
Some are trickier than others depending on what you're doing, but yes.
Sure, but let's assume I can express,
Yep.
router and a couple other things that
So
I need in OVS pipeline.
there are a couple of.
In which case, this approach still gives me advantage.
Well, let me. So when you're looking at this, for example, this will operate at scale at millions of routes for thousands of VRFs, which is a very different thing than what you're usually doing in a match flow offload case, and still continue to perform. So you actually have a performance difference here. But additionally, you can handle stateful features. You can handle a whole bunch of things that are not mechanically programming flows into tables. And part of the reason, actually, and we'll get to this when I get to the architecture slide, part of the reason why we get the massive performance advantage we have is because, in fact, we are not doing a match table mechanism the way OVS and OpenFlow do it. But because we're using a packet processing graph, and some of the things that allows you to do in terms of caching tricks, prefetching tricks, all kinds of other things that are very hard to do in a generic flow table match paradigm, are actually what makes this perform, and also what makes this modular.
Yeah, but as long as it is done in TCAM, arguably your performance.
Until you run out of TCAMs.
Sure, of course.
Yeah. And the other nice thing about this is, again, you brought up hardware that gives you a flow table match. So one of the things we found looking at hardware, I've got a lot of background with the OpenFlow plugin, as some of you are aware. Did a lot of work on that at one point. And one of the things you run into is when you actually try and point at hardware, you discover all kinds of crazy things like, okay, everything here is table 0, so any multi-table thing you have, you can't run with this hardware. This particular hardware has this table for L2 and that table for L3, which means that now you've got to completely refactor your application in order to deal with that particular piece of hardware. And you run into stuff like this again and again and again. Plus, you always run out of TCAMs. And you have to have a good fallback story for what happens when you run out of TCAMs. And if you want to have an application you can deploy in general, you can't always count on their presence, or you can't always count on the same set of them. So you get an exponential explosion of the possible ways your flow programming app could have to deal with a bunch of different hardware. So you can actually take the approach of doing flow programming for a specific piece of hardware, but if you want to write something that runs generally, it ends up producing lots of difficulties for you. Did that answer your question? Yep, cool. Were there other questions before I move on? Yes? No. That's one of the possible projects that people could bring. That was a list of possible things. This slide is actually the features that we currently do have available, which is your standard suite of v4 and v6 features, thousands of VRFs, millions of routes, multiple millions of arbitrary n-tuple classifiers. So if you want to actually classify packets, you can classify them however you'd like, up to millions and millions of classifiers. Counters for absolutely everything, and counters that are semantically meaningful to the thing you're doing. Also, the standard types of tunnels, things in v6 like segment routing and lightweight 4/6. Yep. I can't quite hear you. No, so keep in mind, it is a local bridge, so you have basic bridge tables. But we'll get to that in a second, because when you layer in controller functionality, then you can start having those conversations, right? So very good question. You're just getting a little ahead of me. You see Barrick's fingerprints all over this? If you know Barrick, yes. So you have experience with VPP. Yeah. The build process is easier now. Excellent. So, and then the standard kinds of L2 features that you would want in a switch. Yes?
Sorry, I'm just curious how well VPP will scale if in fact you don't have specialized hardware, you run it essentially in software, because my assumption is if you attempt to do routing with cloud overlays and DPDK, performance will be actually horrible.
So I actually have a slide for that, and the answer is no, it's not. And the reason, again, comes down to the magical ways that VPP is actually processing the packets. So DPDK does a brilliant job of moving those packets from the NIC to the hardware. But when you're in a match table paradigm, you often get yourself into trouble as you try and scale it to more and more complex things, particularly when you're dealing with arbitrary flow tables. But what you'll see here shortly is VPP can handle line rate on 12 10 gig interfaces at 2 million routes. That particular benchmark was not run with overlays. We'd have to get benchmarks for overlays. So I don't have the, we do pretty well on VXLAN. I don't have the numbers in front of me, but so there's a lot that can be done. So really quickly, moving on now to the ever entertaining architecture slide. So as I mentioned, VPP is predicated, it's based on a packet processing graph. And the way that VPP takes advantage of this to be very performant as well as very modular is it takes the entire vector of packets, as many packets as it can get, off of the network I/O layer. And then rather than taking the first packet and running it through the entire graph, and then the second packet and running it through the entire graph. This is what Barrick refers to as scalar packet processing, usually with a disparaging tone. It takes the entire vector and it runs it through the first node. And then it continues to let the graph scheduler move the vector through the graph as a group. Now, vectors may split, because you may get to a point where some packets are handled differently than others. Let's put that particular complexity of the graph scheduler aside for a moment, because it just makes the conversation complicated. But what this does for you is that first packet warms up the iCache and allows you to amateurize a whole lot of your fixed costs across the entire vector of packets. And as a result of this, you end up going enormously faster. You get much faster processing than you would otherwise get, because each of these nodes is doing a very simple fixed task and then handing it off to the next guy. Now, one of the other lovely things about this is it turns out you win in statistics when you do it this way. And by what I mean by win with statistics is, let's say for a moment that you get unlucky. And some of the packets that come through, in fact, more than average number of the packets come through, require more processing. And so you fall a little bit behind. The next vector is quite a bit larger now. So you're taking those fixed costs that you're spreading across the vector, and you're spreading them across a larger N. And so your average cost declines, you tend to catch up. And the result is that you get very reliable throughput and latency through VPP, because the little bit of jitter that you get in processing, you end up winning in statistics because of the properties of the system and the architecture. So that's the basic rundown on the architecture. Now we sort of get to the fun stuff, which is extensibility and modularity. So anybody can bring a project for a plugin, and these plugins can be built independent of the VPP source tree. You just need to install the dev packages for the headers. And they can manipulate the graph node and introduce new nodes. So you see an example of this in the diagram, where I can take a plugin, build it, drop the SO into your particular plugin directory for VPP. It gets loaded, and away you go. And you can do extremely complicated things this way in terms of manipulating the graph node. You mentioned Barrick. He will often observe the only thing you can't do is change the heap size. So then the final piece of this puzzle is hardware support. So one way to think about specialized hardware support is that you have hardware that replaces some of these nodes. It does those tasks for you. Now, that means that you as a hardware vendor, someone who's selling a hardware accelerator, you need to provide a plugin which has an input node. Output nodes are different, but same idea for output nodes, but an input node such that when the processing has occurred in your hardware to the point where you are done with the hardware period of the processing, and you are now moving on to software where you're getting processing that you don't do. Routing lookups are a good one because obviously you want to try and push flows, but at the end of the day, if you haven't pushed a flow or something else down to the hardware, you eventually hit a rib. So at that point, your input node simply hands off to software. Now the beautiful part about this architecturally is if your hardware isn't present, you still have the software nodes. So everything keeps working. And so you don't get the scenario we get today where if I want to take advantage of hardware acceleration, I have to have the extra special magic, it only works with this vendor's hardware piece. What I can have is the stock VPP and a collection of plugins that will take advantage of various vendors' hardware if they're present in order to provide me improved performance. The other thing about this that is awesome if you're somebody looking to build hardware accelerator support is that you're no longer trapped in the match flow table paradigm. If you can think of other cool things to do with hardware, you can take advantage of that and replace nodes with various pieces of what your magic hardware does in order to allow people to accelerate the things that they're doing. So that was a lot on one slide. Do folks have questions? Yes?
Where is the state stored for each plugin?
So typically speaking, the state is not so much associated to the plugin as the graph node, typically. And so basically it's stored in memory. So you may get it, for example, if you look at the IP6 lookup node, it keeps a routing table for V6 routing that has been carefully optimized to be faster than hell at looking up V6 routes. Also has other nice characteristics like in addition to getting an adjacency when you look up a route, you might also discover that you have an alternate next node to be processed in that adds to the flexibility of the system. But it turns out you can actually optimize for particular lookup problems, like a rib, much better than you can for a generalized flow table case. And that's one of the other things you can do to actually help performance here a great deal.
So which plugin has its own memory space?
No, it's a C program. Everyone is basically in the same memory space, but you have APIs. So for example, if I were doing a load balancing plugin, so say those green nodes were a load balancing plugin. And so when someone configured me to have a VIP, I decide that I would like to go and put a route or change the existing route in the routing table for V6 to say, hey, whatever it is that you think you're doing in terms of where you're going, that's cool, but rather than sending yourself off to the IP6 retransmit node, send that VIP here to me so I can do the thing I need to do. And that thing may involve rewriting those headers. For example, if I'm doing a one-armed load balancer where I have to do a 5-tuple match against a session and rewrite the headers so the traffic will come back to me. In that case, I can do that work and I can then dump it back because the graph can be cyclic. Just infinitely cyclic is usually bad. I can dump it back to the IP6 lookup and say, okay, I've rewritten the IP header. I'm going to hand it back to IP6 lookup so that it can actually route where it's going now. Did that answer your question? Cool. Any other questions? I'm sorry, what? So this will run on an x86 server.
But in terms of acceleration?
That's a matter of nodes being provided by various chipset vendors. And we've had a lot of them involved in the conversations around FIDO. So I expect to see some in the not too distant future. But I'm not privy to any concrete plans.
So in general, performance work that's been done has been done on x86?
Yes. Although we also support Cavium, Power, and we've shipped supporting those on actual product. Uh-huh. So structurally, what you have in VPP right now is the VPP project has the infrastructure, and it also has a library of the existing graph nodes that provide those particular sets of features. The expectation is, just because it makes everything scale both technologically and sociologically, is that if people want to add features, they will do separate projects that will bring plugins. It just makes it easier for everyone, because if you're working on, to pick on Gal, if you're working on Lisp and the core VPP guys don't know Lisp from Atom, they shouldn't be reviewing your patches, right? So questions on performance came up. So I do have some slides on performance. So if you look here on the top, that's an L2 switching case. In the back in red, you have VPP. In the front, you have OVS DPDK. So it's all user space, apples to apples. Now, when you're doing a trivial number of MAC addresses, 2, everybody can do line rate, right? That's easy. But as you scale up to more realistic sized bridging tables, what you discover is that VPP continues to perform at line rate. OVS DPDK starts to lose performance rapidly. And this, by the way, is all from an article in Light Reading from independent testing that was done by Eon Tech. I actually have better benchmarks than this, but these are the independently verified ones. They're also a few months old. So now, when you start looking at L3, again, the row in the back is VPP. And you can see going all the way up for IMIX traffic to 12, 10 gig NICs, it continues to mosey along at line rate, even as you scale up to 2 million routes. By way of comparison, even when you get up to something as simple as 1,000 routes with OVS DPDK, you start rapidly losing performance. And 1,000 routes is nothing for a routing table. Yes?
The fifth size is one thing.
Mm-hmm.
When you do the lookup, how many different routes and which part are they? Do you actually go out of cache?
So,
Do you actually have any cache miss, or do you actually use 10 gigabit with the same route, so you end up with the same route?
oh, no, it's a mix of traffic. It's a mix of traffic because, again, if it were 10 gigabits with exactly the same packet going in the same place, it would be uninteresting, and you'd probably see fairly uniform performance. So it's a mix across those addresses in terms of the blips. I do not have this distribution on this slide. If you'd like, I can hook you up with the guy who did the work. He can get it to you.
But that was the case wherein hardware would perform better too, because it won't...
Well, please note, this is not hardware. This is all software.
Right. I mean, OVS
Yeah, yeah.
would perform better too, because then it won't miss the cache either, if it was just going through the same route.
Yeah. I mean, OVS does just fine if it's only looking up the same thing again and again. That's easy for everyone. So, any other questions on this slide before I move on? This is my last performance slide for this. There is, if you guys look online, FIDO has its own YouTube channel, and there's a very detailed talk there about performance that was done by the guy who knows these benchmarks best. And he talks through exactly the methodology, how it's done, everything else. So all the detail you could want is there. So at this point, usually I've talked so much about how beautiful it is to be able to build your own plugins and do modular things that about half the audience usually thinks that VPP is a library by this point. Which is why I paused to point out that it is actually a working vSwitch vRouter that does thousands of VRFs, millions of routes, bridging, tunnel ports. You can program your ARP termination so you don't have to ARP across tunnels. All this stuff works out of the box, at scale, at high performance, semantically.
So what is the dependency on the OS? You say in some slide that there's no dependency on the OS, but then
Well,
it's a switch, then there's got to be something.
that's actually an excellent point. So here's the dependencies. So VPP itself depends on something that looks vaguely like a C library. glibc will work. And DPDK. DPDK will then usually need some kind of UIO mechanism available, but you can use something like UIO PCI generic if you just want something that works generically. So there's actually none of the packet processing is taking place in the kernel. It's all in user space. So DPDK hauls it all up to user space. VPP does all the packet processing in user space, and away you go. So this gets you to the next interesting question. So at this point, everyone should be asking, okay, this is all great. How do I program the damn thing? And the answer is VPP itself exposes a complete low-level API that lets you program all aspects of its feature set. Now, this low-level API is faster than shit, right? Just as an example, you can push 500,000 routes per second into VPP as you're programming it. And in fact, actually, I'm told this number is a little out of date. They're currently getting 750,000 routes per second pushed into VPP, which is pretty good when you think about populating a routing table. Now, it is, however, and this is part of how the performance is achieved, it is done with a shared memory message queue. So obviously, this API is only available locally, but it's available to any external app that is running on the box. So the other really interesting thing here is that the client binding libraries are generated from a .api file, which is a very simple DSL that you can use to generate client bindings. Currently, we have support for generating C client bindings and Java client bindings. But you could add support to generate other language client bindings as well, so that you actually have things that make it relatively straightforward for you to write programs in various languages that talk directly to VPP.
How does VM work? If I want to pass the packet to another VM, how would that work with this?
Oh, so the way it happens to work today is you have an output node. That output node is a vhost user output node, and it uses the vhost user mechanism to talk up to the VM. So that's the way it's currently working. But because you can just have a different output node for that particular interface if you're actually dealing with a different mechanism, if someone comes up with something that's better than vhost user 3 months from now, you write a new output node, everything else stays the same. Yes?
Low-level bindings, you mean that you could implement a node and redirect the graph to it, and the implementation being Java?
No. These are for programming what the data plane does. I mean, don't get me wrong. With enough work, I'm sure you could do what you described, but that's not what I'm talking about. No, these are things like add, delete, modify route, create tunnel tap, create a ton tap interface, connect an interface to a bridge domain, create a bridge domain, delete a bridge domain. These kinds of semantic things that you would program about your features. So yeah, this is the low-level programmability story. In terms of high-level programmability, the model here is that you have a data plane management agent that actually allows you to program from off-box remotely through whatever mechanism is that actually meets your need. So you can have a data plane management agent, runs local to the box. It uses the low-level API to talk to VPP. And it can expose whatever high-level interface you need. NetConf Yang, REST, you can talk to routing protocols like BGP. This is actually critically important. This level of flexibility, you've seen other kinds of data planes that are flexible in terms of what they talk down to, but very rigid about what they will allow you to express as northbound APIs. And what you have here is a very flexible mechanism for expressing high-level northbound APIs. So you can pick the one that actually meets your needs.
Here,
Mm-hmm.
so is the data plane management means really inserting a new plugin graph more in the graph? Or
No, it means saying something like, okay, I'll give you an example. Actually, give me one slide because I have an example. So one of the things that we actually have, please note, multi-project consortium, which means anybody can bring a project to FDio for the data management agent they would like. This is actually one that's been done currently and is an ongoing concern, which is a Honeycomb data plane management agent. So how many folks have heard me babble about Honeycomb over the years in the room? Okay, so 3 years in, we're finally here. The idea with Honeycomb is to strip down OpenDaylight to a very lightweight agent, that just does the particular task you need on the particular box that you need and exposes its APIs northbound. Now, this has a lot of advantages because you get netconf yang for free, you get restconf for free, you have support for programmable BGP if you want that. And so what the current Honeycomb agent is doing, and this is just currently doing bridge domains, is it exposes a Yang model for bridge domains that you can program to. When that comes down into the Honeycomb agent, it uses the Java bindings to call the low-level API in order to stand up those bridge domains, connect tunnels, all those sorts of things. Now, the cool thing that we've done, and I'll talk more about this in the next talk when we talk about Honeycomb, is there's actually a virtual bridge domain application for OpenDaylight as well, which there's a project proposal, it should be coming to ODL proper shortly, that can netconf mount these agents, and you go into that high-level agent, the high-level virtual bridge domain, and say, I would like a virtual bridge domain. Please connect that interface over here, and this interface over there, which happen to be on different switches. It will do the correct things semantically on each one in order to stand that up, and automatically stand up the tunnels so that you get the correct bridge domain. So semantically, you get a topology where you see your virtual bridge domain, you get a topology for its underlay, and you get this very sane view of the world that you can carry forth and actually work with. So rather than having to figure out how to go and program, how many people have been part of the application, the multi-app conversation we've had about getting coexistence working, right? So that conversation just got 1,000,000 times easier, right? Because if I need to do something like load balancing, somebody can bring a plugin, expose an API, expose a model via Yang for Honeycomb, and I don't have to worry about where its flows are going to collide with other flows for other applications because I have the graph to work with. I have semantically meaningful things. And so the probability of collision here is extremely low as a result. Yes?
This is an offline question.
Mm-hmm.
So you're saying that you can strip down the ODL from like, most of the non-required components.
Oh, it can be stripped a lot further, but go on.
To be able to use this as a netconf plus
Mm-hmm.
agent. Is it possible to use this without a VPP, of course, with the same Honeycomb, with just stripping on something as a netconf agent for a switch or a router or?
Oh, no, absolutely you could. You could use it for a switch or a router. You could use it to, you could do the work of having it talk to OVS instead of talk to VPP if that's what you wanted to do, which also has the nice effect that you have a common set of semantic models that work across multiple different implementations.
So right now, the VPP app now, it's what was that, the data model that we showed before, right?
Mm-hmm.
Not the data model, graph.
Yeah, the graph, yeah.
Does the graph need to be exposed as the Yang model?
So not for the applications that I've currently described to you here, no. Could someone come up with an application for which they would want to expose access to the graph? Well, the graph is addressable by the low-level API. You can ask for additional arcs to be drawn on the graph. You can do all kinds of things that affect the existence of graph arcs in the graph via the low-level API. So if you had, and I can't think of one right now, if you had a use case for which that was useful or desirable, it could be done.
The reason why I asked that problem, so the Honeycomb agent is essentially abstracting the VPP implementation from the ODL
Right.
perspective.
So basic things like create a bridge domain, attach interfaces to a bridge domain, stand up tunnels, program bridge table entries, program our termination entries, that kind of stuff.
So for Honeycomb agent, what are the minimum set of projects required?
Minimum set of what?
Minimum set of projects from ODL that are required?
It's basically, so basically you don't need, we happen to be using netconf. So netconf, restconf, MDSAL. AAA also, Ryan, you're always there. You know, that kind of stuff. But basically, think the very, very basic ODL kernel. And in fact, it can be stripped down more than it has. We haven't done the work yet, for example, of stripping it down so it's not using clustering, because at least for the netconf mount case, you wouldn't need clustering in the agent. It's just never going to cluster. Now, you could imagine a scenario where you may have a mega cluster with all these agents clustered together, but that's not the case we're currently doing here. Yeah, you could install those on a Honeycomb agent, totally. In fact, I've talked to people here who are interested in doing that because they'd like to get on board with the Honeycomb approach to things and having a common model for these kinds of functions. Oh no, and wait, there's more. There's more in the next talk.
So does the VPP itself, does it support high availability itself, or do you want to, in that case, we want to be using
Well,
real and XR?
so I think the real question you're asking is, what happens if VPP dies or blows its brains out? And typically the answer is it's a user space process. So if it dies or blows its brains out, it basically takes itself with it. And so you relaunch it. So it's a simple process restart. And in fact, we have deployed this in circumstances where you just have very tight monitoring and a process restart. So you get a very, very small blip when it goes down. Now, obviously, your control plane has to then re-provision what's going on because the data plane itself, not particularly stateful. You really don't want your data planes to be particularly stateful. But it gives you a really, really straightforward answer for recovering from failure. And it also gives you a really straightforward answer for in-service software upgrade. Because if you decide you'd like to go do an upgrade, you don't have to shift the kernel to get new features. You just have to install the new version of VPP and bounce it.
But the user space process side and the read side, you lose the state, right?
Well, so the VPP app itself, its state is intrinsically ephemeral. But your data plane management agent, if you had local state that needed to be reprovisioned, that's what it would have to deal with.
So there's no plans right now about making this itself.
Yeah, the VPP itself is really focused on forwarding traffic, and it's a relatively easy thing to reprogram it from a data plane management agent. So it's a good separation of concerns. Yes?
Does that mean if you want to reconfigure it, you would like shut it down and then restart it? And so it would look like a failure, but now you have a different setup.
No, well, so again, control plane, data plane. The data plane is sitting here, and mostly it knows things like, I have these bridge table entries, I have these route entries, I have this very basic stuff. Your control plane is the thing that would actually be handling the reprogram case. So if I bounce VPP, but the control plane stays up and is smart enough to realize the VPP is come and gone, just comes back and continues program, says, oh crap, you don't know anything, do you? I should tell you. And it tells it all to you again.
I was thinking more like you wanted to get a bunch of data plane, and so you don't want to modify the control plane, and then you want to update.
In principle, yes. In practice, and this is going to sound terribly vain, the data plane doesn't screw up that often. So there are actually very sophisticated tracing mechanisms for API traces to be able to figure out what's come in. And part of the reason those have developed over the years is, again, this is 14 years of history, is you will get people who come and say, your data plane, it is screwing me. Well, what ends up happening 99% of the time is you turn on the API traces and you realize your control plane, it is insane. Not very insane, just a tiny bit insane. A few things that it screwed up in the course of a few million API requests. And so very rarely is the data plane the one that loses its mind. So how am I doing on time, guys? I'm going to just keep going until you make me stop. So again, this is just a really quick look at how you could do VPP and OpenDaylight with OpenStack. Standard story, OpenStack uses the ODL plugin to talk to OpenDaylight. OpenDaylight comes down, and you could use a Honeycomb agent to talk to OVS and VPP. You could have OpenDaylight talk directly to OVS. Either one of those cases would work. Apologies, what time am I supposed to stop, by the way? Okay, so I've got 3 minutes. Other cool things that are going on at FDio. So FDio has what's called the Continuous Performance Lab. This is really cool. So when you care about performance, what you discover very quickly is, number one, you always have to measure performance on real hardware if you want to know whether you've got a performance degradation. VMs don't cut it. Number two, you have a diverse set of hardware you want to be able to measure it against. And then number three, sometimes weird shit happens, and so you'd like to test every single patch as it comes in. So at FDio, we have the Continuous Performance Lab, which is someplace where companies can donate, their servers with their NICs, their particular hardware acceleration, hardware, et cetera. And when a patch comes in to be verified, it'll be built, and performance tests will be run looking for degradation across the CPL. So you can know patch by patch that your performance is not getting worse. In addition, of course, you also have things like continuous functional testing. And then there's we're going to be running a rolling 30-hour benchmark just to get continuous benchmarks of the system so you can see continuous trends on the system's ability to forward performance-wise. Governance, you're all from OpenDaylight. This should look very familiar. Anybody can participate. Anyone can bring a project. Anybody can become a committer via meritocracy. There's a technical steering committee. It basically assists with collaboration and handles project creation reviews and things of that nature. And there's a governing board that oversees budgets, policies, et cetera. So I mentioned possible sub-projects before. These are sub-projects I know are on their way. So obviously the Honeycomb agent should be a project formally shortly. The code is available. We've got Lisp XTR coming so that you'll have XTR functionality for Lisp. And then there is going to shortly be a project for advanced NSH advanced features. How many folks know what NSH is? Okay, cool. So forwarding and doing the cool NSH things you want to do really, really fast. And it'll probably take a couple of months to get those, all that code written in, as opposed to there are other places it's been languishing for years. The way it's going to be structured is the agent itself will live at FDio because it's managing that. And then the controller app will live up at OpenDaylight.
When can we expect that?
Expect the OpenDaylight project?
No, the app.
The project proposal's already in. It hasn't been scheduled for review yet, but the project proposal's in. Yeah, possibly Boron. The reason I was a little bit hesitant is my mind immediately went, is that in 2 months or 6 months? But it's an app, it's not a core piece. So yeah, Boron. Yeah, so you could definitely see it in Boron. And I think the last bit is the call to action to get involved. So there is a lot of collateral up. If you go to FDio, follow the community link. The rest is marketing. Nicely done marketing, but still marketing. That'll take you to the wiki where you can get instructions on how to get the code, build it, and run it. The good news is the building is now really, really easy. There's a Vagrant directory. You type Vagrant up. It constructs a box that will build. It builds, and then it cats you a README file that tells you how to play with it. So, soup to nuts pretty quick. There are an enormous number of both written and video tutorials. We have several days worth of detailed technical deep dive tutorials on YouTube where you can dive in. And the good news is they're segmented into bite-sized chunks. So if you want to go see 40 minutes on how to really drill into building the API, the low-level API for your plugin, you can drill into that. If you want to go spend 20 minutes learning about a walkthrough of how you would actually construct and build a plugin, there's that. If you want to see an hour of details about how benchmarking has been performed in the results, that's there as well. And then we have the traditional sort of communication channels. There are mailing lists, there are IRC channels, and there's a pretty detailed wiki thus far, and it's only growing. So, last slide. More questions? Yes? There's a story there for another time. But yeah, no, you can just go to fd.io, and that will take you to the main webpage. And the wiki is wiki.fd.io, and Garrett is garrett.fd.io, and Jenkins, and all the usual suspects. For those of you who've been part of the Bugzilla versus Jira conversation, there's jira.fd.io as well. So we are using Jira for bug tracking. Other questions? These slides, not yet. As soon as I get someone in ODL to tell me where to put them, and actually you make a good point, I should put together a presentation page and stick them up there. But thank you for poking me about that. Anything else?
So you declared the graph. There's the loop. Is that something that
So in terms of the graph, So this is often referred to as programming for responsible adults. If you're going to introduce a cycle into the graph, you should do something to make sure that it's not infinite. So for example, if you get a packet from IP lookup and you change its IP address and you hand it back to IP lookup, that's kosher. If you get a packet and you don't change its IP address and you hand it back to IP6 lookup, that's going to go badly for everyone. Oh no, dude, there's no end to the creative ways in which you can blow your brains out in the world. Programming for consenting adults. So, any other questions before we break? And I want to figure out logistics of my next talk, for which I have a demo video. Good. So thank you all for coming. Happy to answer any other questions you have in the course of the rest of the time I'm here the next couple days.